Welcome to this lesson on probably one of the more daunting concepts for GMAT test takers who haven't had a math class in a while, plane geometry. So let's begin with the basics, starting with lines. Now, a line is assumed in the plane to be infinite unless it's designated as a line segment. And if you're talking about a line segment, it is technically the shortest distance between any 2 points. Pardon me, in the coordinate plane. Now, it is assumed to be a straight line unless it is otherwise indicated. So if you're looking at a line, you go, that is a straight line unless they indicate that it isn't, or as you can see in the bottom right of this slide, there's a circle, and that definitely is not a straight line. Now, parallel is going to indicate that two lines will never intersect in the plane, and that is indicated by those two vertical lines there on the screen. And when you have two parallel lines intersected by a third line, which is called a transversal, that's going to create congruent angles in identical positions. So if you've got a third line cutting through two parallel lines, you know that all the small angles are equal to all the small angles, all the big angles are equal to the big angles, and any big angle plus any small angle will equal 180. Now, a perpendicular intersection is indicated by that upside down T symbol or potentially a little just corner in an angle, and that indicates the two lines intersect at a 90-degree angle. And perpendicular lines that continue after intersection create equal angles at the point of intersection, because 90 plus 90 plus 90 plus 90 is equal to 360. So the sum of the angles on one side of a line, as we just kind of alluded to, is always going to be 180 degrees, no matter the number of angles that you're looking at. And the strategic implications of these rules of lines are first that you want to seek to add or extend line segments to discover easy shapes and relationships in a figure if you decide to draw your own figure for a GMAT geometry problem. And we'll talk about the implications of drawing here in a little bit as well, because you may or may not want to do it based on the structure of the problem. But you also, even if you do draw, want to minimize the number of line segments by strategically considering where it's best to extend or add a line. You don't want to just add a bunch of lines and overcomplicate the figure. You want to stay simple and think strategically about where best to add lines potentially to help find an easy shape or relationship. Now, the cousin of lines that dictate everything else in plane geometry are going to be angles. And angles measure the distance between two intersecting lines in what are known as degrees. So the sum of degrees around any single point is going to be 360, and that's because if you put a point kind of with your finger there, you draw around it, you create a circle. There's your 360 degrees. We also have just some names that you'll need to know that relate to the quantities of degree measurements. Acute means that an angle is less than 90 degrees. Right means that an angle is exactly 90 degrees. Obtuse means that the angle's measurement is greater than 90 degrees but less than 180 degrees, because 180 degrees is going to be what is known as a straight angle. And vertical angles are what are created by opposing sides of intersecting lines. So you can see here with the little figure that just popped up that x's, the x degree measurements here, those are equal. And you may think to yourself, well, the x's are vertical, but the y's are not. Well, the vertical is a little bit of a deceptive term here. It just means opposing. And so the y's are also quote unquote vertical angles. You can just think of them as opposite angles, and they're created on the other side of intersecting lines always. Now, here are some strategic implications about angles. First, don't assume that angles, lines, or anything else are drawn to scale on the GMAT. You have to actually only trust what's written, so be very skeptical of just how it looks. And you can only rely upon formulas and rules to define relationships between angles or lines for that reason. For instance, using this figure that we just drew out, we know that x plus y, if this figure were on the GMAT, is absolutely going to add to 180 because the sum of the degrees on any side of a straight line is 180. But x itself, or y itself for that matter, may or may not be greater than, less than, or equal to 90. We can't tell without additional information because you can't assume that those angles were actually scaled properly on the exam as pertains to plane geometry figures that they provide. Now, on to the simplest of shapes, a triangle. It is a polygon with three sides, and the sum of its interior angles is equal to the sum on one side of a line at 180 degrees. An isosceles triangle has two congruent sides which oppose two congruent angles. And congruent just means equal in fancy geometry terminology. Equilateral means that all sides in the triangle are congruent, as are each interior angle, and those interior angles are going to be 60 degrees each because 180 divided by 3, of course, is 60 degrees. Then we get to acute, which indicates that each angle in the triangle is less than 90 degrees. So you can define your triangle similarly to what you do with the angles themselves, because a right triangle just means that one angle has 90 degrees, has a measurement of 90 degrees. And of course, it can only be one angle that has the measurement of 90 degrees, because if you had two angles with a measurement of 90 degrees, you have a straight line and you would not be able to form a triangle. Similarly, you can only have one angle that would be obtuse, and thereby name your triangle as obtuse. Now, you also can have an exterior angle of any triangle with just extending the line past the vertex for one of them, and that is going to be equal to the sum of opposing interior angles. And we can see that illustrated here. So we've got some angle measurements written out. And we know that a plus z is equal to 180 because that's the sum of the degrees on one side of a line. We also know that x plus y plus z is equal to 180. And because of those facts, we know that we can basically just say that x plus y has to equal a, because if z plus that quantity is equal to 180 and z plus that quantity is equal to 180, those two quantities have to be equal. So hence why the exterior angle is always equal to the sum of the opposing interior angles for any triangle. We also know that angles within a triangle are proportional to their opposing sides. So the shortest side is always going to oppose the smallest angle. Now, I just got done saying don't trust the figure, but just using this figure as an exemplar, we could see that clearly the side opposing y's angle is the shortest. That means that y will be the smallest angle of the triangle. We also know that if you've got equal sides, hence the isosceles and equilateral rules, those are going to oppose equal angles. Your largest side or longest side is going to oppose the largest angle. So we just know that that proportionality is consistent for triangles. And there are a couple of formulas that you need to know for triangles as well. First, you need to know that the area is going to be 1/2 times the base times the height, where the base has to be perpendicular to the height. So you couldn't just take two sides of the triangles that are on this figure and use them to find the area unless you knew definitively that they intersected at a 90-degree angle. We also have what is known as the third side rule, or the triangle inequality is what they actually call it, wherein the third side of a triangle always has to be less than the sum of the other two sides, and greater than the difference of the other two sides. Because if your third side is greater than the sum of the other two sides, or equal to, then you just have a straight line or overlap. And if it's not greater than the distance of the other two sides, the difference of the other two sides, then you're not going to have a line long enough to connect the other two sides. So now let's talk about probably the most famous of all theorems, the Pythagorean theorem. So the Pythagorean theorem is a squared plus b squared equals c squared. Most people know it as such. And the Pythagorean theorem actually defines a right triangle. So when a squared plus b squared is equal to c squared, we know we have a right triangle where c is the length of the longest side, which is known as the hypotenuse. But we also can derive a few other facts from the Pythagorean theorem itself. If a squared plus b squared is less than c squared, we're looking at an obtuse triangle, because what's happening with c squared is it's getting bigger, which means that we would expand our 90-degree angle beyond 90 degrees to create an angle beyond 90 degrees, so it would have to be an obtuse triangle if a squared plus b squared is less than c squared. Conversely, if a squared plus b squared is greater than c squared, then we have to have an acute triangle, because what has happened is we have shrunk proportionally the c squared side, and that means we shrink the 90-degree angle, and all the angles are going to be less than 90 degrees, and thereby it would be an acute triangle. Now we'll talk briefly about what are known as the Pythagorean integer triples, and some of these may be familiar to you. They are going to be integer values of side lengths of a right triangle that satisfy the Pythagorean theorem, meaning that this integer squared plus that integer squared equals another third integer squared. One thing to note, though, is that your Pythagorean integer triples cannot simultaneously be what are commonly known as your special right triangles that we'll talk about in a moment. They cannot be an isosceles right triangle, nor can they be half an equilateral triangle, because if that were the case, they would have different proportions that we'll talk about momentarily. So, the most common triples you may recognize: particularly 3, 4, 5, because 3 squared, 9, plus 4 squared, 16 is 25, which is 5 squared. Also, you'll probably want to commit to memory 5 squared, or 5, 12, and 13, because 25 plus 144 is, in fact, going to be 169. There are some rarer triples that you may want to commit to memory as well, 8, 15, 17, and 7, 24, 25. Multiples of these integer triples will work too. So that means that 6, 8, 10, because that's just 3 times 2, 4 times 2, 5 times 2, and 50, 120, 130 will also work because those are just multiples of the triples that already exist. So now let's talk about these special right triangles, starting with an isosceles right triangle. So we've got an isosceles right triangle on the screen, and ultimately that 45, 45, 90, x, x, x root 2 is what we want to commit to memory as a ratio that works for all isosceles right triangles. So to solve for the sides of an isosceles right triangle, instead of having a squared plus b squared equals c squared, you can see on the figure that because we've got two 45-degree angles, we know that they oppose equal sides. So that means we really just have a and a c, which means that we can rewrite the a squared plus b squared equals c squared equation as a squared plus a squared equals c squared. We just combine the like terms then. 2a squared equals c squared. Then we square root the full equation to find that a root 2 is equal to c. And that popped into the figure as well. And that means that and proves that our constant ratio of the opposing sides in an isosceles 45, 45, 90 degree right triangle is x, x, x radical 2. So if you know one of the sides, you'll be able to find all of the others using this ratio. Then we've got half of an equilateral triangle as the other of our special right triangles. So we can see an equilateral triangle on the screen. And to solve for the side of half of an equilateral triangle, we just draw a vertical line down the middle, and then we've got a 30, 60, 90 right triangle. Because we originally had 60, 60, 60 as our degree measurement. So if we split the apex in half, we create a 30-degree angle on the right-hand side, and the left-hand side for that matter. And then we've got 90-degree angles at the base. So we've got a 30, 60, 90 right triangle. And by the definition of an equilateral right triangle, instead of having a squared plus b squared equals c squared, we know that our original blue sides were all the same. So we halved our short side from one of the original sides, so we know that our short side of A is exactly half of the longest side, the 90-degree opposing side, the hypotenuse of 2A. And then we just keep the b. So then we want to distribute the exponent to the right side quantity first. And so we can see that that becomes a squared plus b squared equals 4a squared. Then we want to subtract a squared from each side. We have b squared is equal to 3a squared. Then we square root the full equation again and discover that b is equal to a radical 3, which produces our constant ratio of opposing sides in half of an equilateral triangle, the 30, 60, 90 right triangle, of x, x radical 3, and 2x. So once again, if you have any of the sides in a 30, 60, 90 right triangle, you can derive the other sides as well using this ratio. So now we'll talk about some GMAT polygons. First off, well, other polygons beyond a triangle. We know that all GMAT polygons are defined as convex unless they are otherwise designated. So what does that mean? That means that every interior angle of a GMAT polygon is under 180 degrees unless it's otherwise designated. They might say that you've got a weird shape, but they will tell you explicitly, or they will say that this is not convex, drawn to scale, something of that nature. So assume everything is under 180 degrees in terms of the interior angles otherwise. Now, regular as a term for polygons just means that all the sides in each of the interior angles are congruent or the same. And the sum of interior degrees for any polygon can be derived from this formula. N minus 2 times 180, where n is just equal to the number of the sides in a polygon. We'll run off a bunch of different degree measurements just based on the names of polygons that you probably should commit to memory just in case they show up on the test. But in a pinch, you can definitely just use this formula. So a quadrilateral is our default four-sided shape. We cannot assume it's a square. We cannot assume it's a parallelogram even. We just know that it's a quadrilateral if it has four sides. And the sum of the interior angles is always going to be 360 degrees. A pentagon is going to have 5 sides. And the sum of the interior angles there will be 540 degrees. A hexagon will have 6 sides. Sum of the interior angles there is going to be 720 degrees. A heptagon or a septagon is 7 sides. And the sum of the interior angles is 900 degrees. An octagon has 8 sides with a sum of interior angles of 1080 degrees. A nonagon has 9 sides, and that's when the sum of the interior angles is 1260 degrees. And a decagon, which you might recognize from the term decade, has 10 sides, and the sum of interior angles there is 1440 degrees. Now, you may also note that there is a constant difference of 180 degrees when we increase the number of sides. And that's because there is 180 degrees on one side of a line. So if you add a side, you add 180 degrees. So if you ever forget that sum of interior degrees formula, you could potentially just add 180 for every side beyond a triangle in your shape that you're evaluating. So let's move on from these polygons to a special set of quadrilaterals. So we just learned that a quadrilateral has 360 degrees in its sum of its interior degrees, and we know that it has 4 sides. So the first of our special quadrilaterals, and it too has 4 sides and 360 interior degrees, is what is known as a parallelogram. And it gets that name because its opposing sides are parallel. And because those opposing sides are parallel, we know that they are congruent, as are the opposing angles, just from the rules of creating a intersecting lines with a transversal in 2 sets of parallel lines. We know that the sum of any 2 adjacent angles in a parallelogram is also going to be 180 degrees. And we know that the diagonals created from opposing angles in a parallelogram will create congruent triangles as well. Now, the formulas you'll need for a parallelogram: first, the area is going to be just the base times the height, but because a parallelogram does not necessarily have to be perpendicular, you have to make sure that you draw a vertical line that will be perpendicular to whatever you define as your base. We also know that the formula for a parallelogram's perimeter is just going to be 2 times the length plus the width distributed. Then we have what is known as a rectangle. And a rectangle is going to be an equiangular parallelogram. So all the facts about a parallelogram are also true about a rectangle, with the added caveat that each interior angle in a rectangle is 90 degrees itself. And that means we can actually shorthand now our area formula, because it's just length times width. Because the angles, the vertexes of the rectangle themselves are known to be 90 degrees by definition, we don't have to calculate base and height anymore, or draw base and height anymore. But the perimeter formula is going to remain the same, just 2 times length plus width. Now, a square is a regular quadrilateral, meaning that it has all congruent sides and angles. So it's basically 90 degrees all the way around, and it's got the same sides. So we can shorthand our area and perimeter formulas even further with a square. We know that the area is going to be equal to just any side raised to the second power, because it's just side times side, or squared, hence the term for a power of 2. And the perimeter is simply just 4 times any of the sides. Now, a trapezoid is the last of our unique quadrilaterals that you might find on the GMAT, but it is not a parallelogram. It's simply a quadrilateral with a single pair of parallel sides that are known as the bases. And there's one thing you can do with a trapezoid, which is find its area. And you do that by finding 1/2 times the sum of the bases times the height. So you add up the 2 parallel side lengths, divided by 2, and multiply by the height, where once again the base has to be perpendicular to the height, because the sides of the trapezoid itself, the non-base sides, are known to not in fact be perpendicular to the other 2 parallel bases. So then we move on to circles, and circles are just a set of points equidistant from a defined center. And a chord is any line segment with endpoints on a circle. Now, your diameter is technically your longest possible chord that passes through the center of your circle. So it's one of those scenarios where all diameters are chords, but not all chords are diameters. Now, a radius is probably the most important measurement for any circle, and it's the distance from your center to any point on the circle. It is equal to half of the diameter, and you need to remember that all radii are equal for any individual circle. So wherever you draw a radius, it's the same distance from that center to any point on the circle. Now, an arc is just a partial distance around a circle defined by what is known as a central angle, and we'll talk about that here in a moment a little bit more. But that distance around the circle is fancy for a circle, it's the circumference, and that's equal to 2 times pi times r, or pi times the diameter. And your area formula for a circle is just pi times the radius squared. Definitely commit both of those formulas to memory. Now, the strategic implications for circles: if you are drawing a circle as part of your process, make sure you include a center. You absolutely need to have a center for any circle, because that is what relates the circle to anything else. So always include centers if you're drawing circles. And if you're looking at an inscribed, which means that you've got a figure inside of another figure, or a circumscribed figure, which means that you've got a figure outside of another figure, you want to look for methods of relating that other shape to a circle. So drawing lines, adding lines, doing something to relate the two shapes to each other. So just something else to think about if you see a complex geometry problem involving a circle. So lastly, we'll just talk about the circle proportionality. So we know that our central angle out of 360 is equal to our arc length out of the circumference, or 2 pi r, or equal to our sector area out of the total area, which is pi r squared, because the total degree measurement is 360. So we know that that central angle out of 360 gives us the fraction of the arc length out of the total circumference, or that sector area, the pi piece, out of the total area. So let's just take a look at an example. So what would be the arc length created by a 36-degree central angle in a circle with a radius of 10? So we first just set up the proportion. We've got 36 out of 360 is equal to the arc length out of 2 pi times the radius we just found out of 10. Then all we have to do is reduce the fraction and cross multiply to find that our arc length is going to be 1/10, because 36 out of 360 is just 1/10. Simplifies down quite easily, as many of these problems will if you understand the rules of geometry. And then we've just moved that 2 pi times 10, or 20 pi, over to the left-hand side to find that our arc is going to be equal to just 2 pi, or 1/10 of the 20 pi that is the circumference of the entire circle. So now that we've talked about the basic shapes that you'll encounter in plane geometry, let's talk about our geometry quantitative problem process holistically. So step one is going to be to just set up your scratchpad as appropriate for either a standard problem solving or data sufficiency question. Really, everything that we're going to talk about here in these steps are just additions to what you've already learned. Step two is going to be to read the problem from the beginning, taking notes as necessary, and you want to determine consciously at the end if drawing any figures to scale would be helpful. Generally, it's going to be more helpful if real numbers are provided in the problem, and or you have complex shapes that you would benefit from being able to kind of add lines, find out relationships manually yourself. However, it's generally going to be assumed that it's less helpful to draw if no real numbers are provided, and or you have simple shapes that you should be able to evaluate formulaically, because you know how a triangle works, you know how a parallelogram works, and so on and so forth. And remember that if you're going to draw, it is going to potentially be a little bit of a time-consuming process, so you want to consider whether or not that figure is necessary or helpful. Then remember that you can only trust the written information, not how it looks when it comes to plane geometry figures. So you have to make sure that you incorporate the written information, not just how it looks, if you're going to draw. And that's partly why you don't want to draw if there isn't known values or known facts about the figure that will help you to draw it to scale, because your drawing actually may end up being incorrect and make some assumptions that aren't warranted. But if you decide that drawing is the best approach, first you want to carefully draw the figure to scale based on the information that's provided, labeling all known and deducible values for the figure. So what that means is, if they give you some labels and they say, this is a side length of 10, write that down. But also try to think about what other things you know based on some of the rules that we've talked about in this lesson. So the things that you want to label as best you can are values for lengths, values for angle degree measurements, values for areas, values for volumes if you're in a three-dimensional figure, and we'll talk more about three-dimensional figures in another lesson, as we will about coordinate points. So if you draw the coordinate plane, you're probably doing that because they don't have a coordinate plane for you to reference, and you can draw that to scale pretty easily because you know the coordinate plane has to be scaled in order for you to be able to manipulate it in any meaningful sort of way. So you might include coordinate points if you're trying to see visually what the relationship is for a problem if they don't give you a coordinate plane drawing for you to reference on the question itself. Then step 4 You want to write out all needed formulas for the problem and or your drawn figure, and that's to make sure that you can plug in easily to the formulas that are required from your figure or from the problem. A lot of geometry is really just algebra in a different coat. So you want to make sure that you have those formulas preemptively written out so that you can relate back to them as the problem dictates. And then step 5, you want to work the problem as normal following your appropriate process, whether it's problem solving or data sufficiency. So for problem solving, you want to consider all 4 possible tactics, especially logical estimation. There are probably more opportunities for logical estimation in geometry questions, problem solving questions, that is, than anywhere else in the problem solving section of the GMAT. So really lean into logical estimation if you aren't able to technically solve any GMAT geometry problems. For data sufficiencies, you want to rely on the algebra. So seek to articulate what is known, needed, and provided by the conditions as algebraically as possible to most efficiently evaluate those statements. And lastly, when you're working the problem, leave your calculations in irrational, that's usually pi or radical notation, unless you are asked to approximate. Note your answer choices if they have pi's, if they have radicals in there. Do not automatically convert those values into decimals. It will actually make things much more difficult for you to evaluate. Instead, just leave them as pi's or square roots, unless you are asked specifically to approximate. In which case, you probably already know that pi is approximately 3.14 as a decimal. That is as far as you'll need to go for the purposes of this exam. You don't keep going down 1.5 and so on and so forth. Square root of 2 is approximately 1.4. And the square root of 3 is approximately 1.7. Again, you can go further than that, but it's probably not necessary on this exam. And if you happen to be in a Western country that celebrates St. Patrick's and St. Valentine's Days, that's a helpful little mnemonic to keep track of what the square root of 2 and square root of 3 is. Square root of 2 is February 14th, 214. Square root of 3 is March 17, 317, just with a decimal in the middle. So just a whole bunch of plain geometry tips here. Let's move on over to the whiteboard and take a look at an example and how we can use a lot of this information to solve some of these geometry problems on the GMAT quantitative section. Let's take a look at a sample problem solving question to start. And as always, we just set up our scratch pad, got A, B, C, D, E here. Set up the line over top to put where we are looking to place our sought value. So we skip to the end. We're being asked for the area of the shaded region. So shaded area, and we got 24, 40, 48, 60, and 120 as our possible answers. So start taking notes as we go, and again, I've got to decide consciously whether or not I want to fully draw this thing out. So in the pentagon above, we've got WV is equal to 12, okay? And the shaded region is clearly a triangle. So I need my formula for area of a triangle, which is 1/2 base times height is going to be the shaded area. And you always want to focus on what you're being asked for. And in this case, it's the easiest to find the shaded area by just going straight at it. But there are instances where the shaded area may be more easily solved for by solving for the total in the unshaded. So it's just a kind of an added bonus here that the shaded area is often going to be equal to my total minus my unshaded. And if you're ever asked for a less familiar shape, your unfamiliar value on the GMAT is frequently equal to your total minus whatever the familiar is. But again, we've got a triangle as our shaded shape here, so it's a little bit more straightforward. So then we're told that WV is 12, so that can be my base. So my base of WV is equal to 12, okay? And TV is equal to 10. Okay, so we've got TV is equal to 10, my base WV is equal to 12, and so if we were to consider this, I could, and this is where you might decide to draw it out, and I'll just kind of cheat a hair since I've got it on the screen, but you might draw it out because if you draw a dotted line here, you get a right angle. and I'd split that WV exactly in half, and I'd have 6 here, and I'd have 10 here. And remember what we said, if they are giving you real values in a complex shape, it may be in your best interest to draw this. So then we've got 6 and 10, and this is one of our Pythagorean integer triples. So we know that our height, undefined like by a variable as it may be, is just equal to 8 because that's a 6, 8, 10 right triangle. So that means our formula is just going to be 1/2 times 12 times 8. And that's going to be 6 times 8, which is 48. And our answer is choice C. So you can see potentially drawing this would help. Noting how to solve for shaded areas will also be helpful as we move along. But let's take a look next at a data sufficiency problem. So we've got one here of every side of a triangle. So not a lot to go on this problem, but we just start out with what we know. And we know we've got a triangle. So we've got triangle DEF. And we want to know, is each side less than 10? And of course, this is a yes-no data sufficiency, so we note that, we box it off. So what we need is going to be that third side rule, because is DE, we'll just put it in the middle. Or sorry, not DE, but any side. I'm going to cut myself looking ahead to the first condition. Be careful of that, of course. Is any side less than the sum of the other two and greater than the difference of the other two? So condition 1 tells us the aforementioned DE is equal to 5. Okay. And this is where it may be beneficial to consider drawing again. It's really easy for me to say, well, it could just be an equilateral triangle 5, 5, 5, and the answer would be yes, everything is less than 10. But I could also have just a couple of really long sides here and say that's 15, 15, and 5. Because 5 would be greater than the difference of the other two, which would be 0, and it would be less than the sum of the other two, which would be 30. So no matter what we're doing, this is all fine so far. So that's not sufficient. Our options, of course, remain B, C, or E. Then condition 2 tells me that DEF is isosceles. So that tells me that two of the sides are the same, but I don't know any of the side values here, though. So that's out. And when we combine the two, since we've drawn some relatively simple figures, since we had real numbers to work with, I can see pretty quickly that this isn't sufficient either, because I could have 15, 15, and 5 still, because 15, 15, 5 is isosceles, and there's my no, and my yes, 5, 5, and 5 is equilateral, but technically it's also isosceles, so this too would work, and our answer at this point is E. So there's just a couple of examples. There are plenty more out there for you to practice on your own, so go ahead and do some quantitative drills involving geometry and apply all of the tactics and all of the concepts that we've covered here in this lesson.